Alright, coming at you with take 2 of the Chapter 2 homework review. Apparently the first time I recorded it, the software had some settings that were incorrect, and I did not get any audio in that first video, so that was probably a pretty useless video for the few of you that watched it. So let me try this again, and it should go better this time. Alright, so getting into it, let's open up the file. Alright, so we're going to go over about 8 or so questions. Some of these were requests from students. Some of these were ones that I identified as people having trouble with based on the average scores that we got on Blackboard. The overall average score for this week for the section was, I think, 9.93 out of 12. So, pretty good, but the assignments are getting tougher, so naturally the scores are going down a little bit. Nothing to be concerned about with that score, but of course, a lot of topics covered, a lot of important types of problems that we had, so it's good for you to ask any questions you have from me. Alright, so then let's get into the questions. So the first few questions are requests for students, and they all deal with ionization energies. So we learned a periodic trend for ionization energy. If you recall, that trend is basically that the ionization energy increases as we move up a column, and it also increases as we move left to right. There's some slight blips in that trend. So for example, group 2 has an abnormally high ionization energy, so group 2 ionization energies are larger than group 3, even though group 3 is to the right of group 2. And then same thing between group 5 and group 6. Group 5 has that relatively stable P3 configuration, so its ionization energy is larger than you'd expect, doesn't want to lose an electron, so group 5 ionization energies are typically larger than group 6. Again, even though we're moving left to right, that's a little bit of a break in the trend. So those things may come up in some of these questions, but I think on this one, the bigger issue was how do we deal with second ionization energy? So what we're looking for here is which of the following atoms would have the largest second ionization energy? And so anytime we're doing an ionization energy that's greater than the first, that periodic trend only works for the first ionization energy, which is removing the first electron. If we want to do it for second, third, fourth, fifth, whatever ionization energy, anything beyond the first one, we have to first look at the number of valence electrons. So that's going to be our strategy in these types of problems. And the reason for that is if you're removing valence electrons, the first ionization energy will always be a valence electron because everything has at least one valence electron. But if you're removing valence electrons, in general, that's relatively easy to do. Again, they're not all as easy as each other, and each time we remove an electron, it becomes more difficult to remove the next one. But anything that's in the valence shell is relatively easy to remove. But if you start talking about core electrons, those are the ones that are beyond valence electrons, or the ones that are in that noble gas core configuration. Those are relatively difficult to remove. And so these would have then some pretty significant differences in their ionization energy. So valence electrons are relatively easy to remove, core electrons are relatively difficult, or I should say very difficult to remove, which means that once you start getting to core electrons, you expect the ionization energy to jump by a lot. So if we're looking at the second ionization energy, we should first figure out for these 5 elements here, how many of those does the second ionization energy involve valence electrons versus how many involve core electrons. Alright, so then if we go to if we go back to the periodic table, if we go to the periodic table here, we look at the ones that we're comparing, and these are all main group elements. They're all in these A groups on the periodic table. So we can basically use the periodic table to figure out how many valence electrons these have quite easily. So we have the first one's magnesium, and we also have calcium as part of this. So if we look at magnesium and calcium, those are both in group 2A, and that means they both have 2 valence electrons. So I'm going to write the number of valence electrons next to each of these, 2 for each of those. We have chlorine and sulfur. Those are both right next to each other on the periodic table, so let's find out how many valence electrons those have. So chlorine is here in group 7, so it would have 7 valence electrons. Sulfur is right next to it to the left, which is group 6, so it has 6 valence electrons. And so that means those two are going to have 7 and 6. And then finally, sodium, which is the last one on here, Na, we find that in the periodic table. And Na is, wrong document. Sodium, Na is here in group 1, so sodium has only 1 valence electron. So then looking at these answer choices, remember that second ionization energy refers to removing the second electron. So for magnesium, the second ionization energy is going to remove the second valence electron. Chlorine and sulfur, we're still removing valence electrons. Calcium, second ionization energy is removing a valence electron. But for sodium, we only have one valence electron. So the second ionization energy is going to involve core electrons, or removing one core electron specifically. So that we would expect to be very difficult, and that means sodium for its second ionization energy should be very high. So that's going to be our obvious answer choice when that's the only one that involves removing core electrons. If we were comparing two atoms where we're removing core electrons from both, or two atoms where we're removing valence electrons from both, and it's not the first ionization energy, and we want to think about which one's higher or lower, it's not always straightforward to do, but we would still rely on the periodic trends that we have. But the periodic trends really only work for first ionization energy, and in this case, if we're removing core electrons, you would want to identify that automatically as the highest. All right. So this next question also deals with ionization energies here for magnesium, Mg, and the question from the student specifically referred to how do we again deal with cations in this situation. So this answer choice E here involves comparing ionization energies of magnesium to a cation Mg+. How does that factor into these comparisons? So let's talk about all these answer choices as well. So the first one here, A, we're looking for the statement that's not true. So the first one, A, the ionization energy of magnesium is lower than that of sodium. If we go to the periodic table and find magnesium and sodium, they're arranged left to right. Magnesium is to the right of sodium. It's in group 2, which has especially high ionization energies. So we would expect magnesium to have a higher ionization energy than sodium. And this statement here says that it's lower. So magnesium should be higher than sodium in ionization energy. So this statement is not true. So we think that's going to be our answer, although we should verify that the rest of these answer choices are also false, just at least for peace of mind. So A should be false. If we look at choice B, I don't need to write it twice. For choice B here, ionization energy of magnesium versus neon. Magnesium is here, neon is up here. So magnesium is both to the right and above magnesium. So just on the basis of the general trend, we expect neon to be higher. Also, neon is one of these noble gases which have exceptionally high ionization energies. So neon we would definitely expect to be larger than any of these metals over here. So that statement is true. Magnesium should be lower than neon. Is magnesium lower than beryllium? So beryllium is Be. That's the element right above magnesium. Ionization energy increases as we go up, so beryllium should be higher than magnesium, or magnesium lower than beryllium. So that statement is true, so we're good on that one. And then magnesium ionization energy is higher than that of calcium. So calcium is Ca, it's right below magnesium. Magnesium would be a higher ionization energy than calcium because, again, it's above in the same column. So as we're going through the column, the ionization energy would decrease as we go beryllium, magnesium, calcium, strontium, barium. So Ca, calcium, is definitely a smaller ionization energy than magnesium, so this statement is true. And then finally, the answer choice that caused the most confusion, how do we compare magnesium and magnesium plus? And what the student that sent this question in asked, which is a good point, is that magnesium plus, if we look at the periodic table, Mg plus would remove one electron, so it'd have the same number of electrons as sodium. They both have 11 electrons. So why does magnesium plus have a different ionization energy than sodium? Why is the comparison of, why are choices A and E even different from each other? Now there's two ways to go about addressing this point. So first is, in choices A and E, they is comparing magnesium to sodium and Mg plus. Well, let's compare the ionization energies of sodium versus Mg plus. So they both have 11 electrons, but sodium has 11 protons also when it's neutral, but magnesium plus would still have 12 protons. So between magnesium plus and sodium, we would expect that this one has 12 protons, this one has 11. This is going to hold on to electrons more tightly. There's a stronger attraction to that valence electron from these 12 protons. So between these two, this one, magnesium plus, should have the higher ionization energy. So whenever we compare species that have the same number of electrons like these do, the one that has more protons has higher ionization energies. Now that doesn't necessarily answer this question though, because here we're looking at just magnesium neutral to magnesium plus. So for magnesium, the ionization energy would be the first ionization energy. And then for a magnesium plus, we're removing another electron, so that's technically the second ionization energy of magnesium. And so for any given element, the first ionization energy is the smallest, and then the second, and then the third, and so on. Alright, so you have this trend where if you're comparing the same element, magnesium in this case, the first ionization energy is the smallest, then second, then third. Somewhere there's going to be a big jump once we go to the core electrons, but they're all going to monotonically increase as we go to successive ones. So in other words, removing electrons from cations is more difficult than removing them from neutral atoms. So in this case, we would expect that the magnesium ionization energy is lower than Mg+. That is also true, because the ionization energy for magnesium plus is the same as saying the second ionization energy of magnesium, which is definitely going to be bigger than its first. So the only false statement then would be A. The only not true statement as it's worded in this question. All right, next one. More things about periodic trends, again, mostly with ionization energies. So which of the following statements is true, A, B, C, and D? So for A, we're comparing the first ionization potential, that should be energy, same thing. First ionization energy of hydrogen and helium. And we're looking for the false statement. So hydrogen and helium are the first two elements on the periodic table. Hydrogen on atomic number 1, helium 2. Helium is to the right of hydrogen. They have the same valence electrons. So we would expect helium to have a higher ionization energy than hydrogen. So hydrogen should have a smaller ionization energy. Here it says that this is greater, so this statement is going to be false. The ionization of energy of hydrogen should be smaller than helium because helium is to the right, helium is a noble gas. However you want to think about that, they both factor into that having a higher ionization energy than hydrogen. Choice B, I think, was the one that gave this student the most confusion, which is the ionic radius. So here we're talking about the size of atoms, and again we have a periodic trend for that. Radius increases right to left, increases as we go top to bottom. But once again, if we're dealing with ions, we can't necessarily just think about the periodic trend. We have to think about number of electrons, number of protons, and so on. So in general, and I think there's no exception to this that I know of, if you're comparing ionic radius and is for the same element, so for a given element, the higher the charge that you have on the ion, positive charge I should say, corresponds with a smaller radius. So the more positive charge you have, the smaller the radius would be. Every time you remove an electron, you're taking away an outer electron. You have more protons. You have still the same number of protons in the nucleus to attract those fewer electrons. So every time you remove an electron, the radius contracts. So in this case, we would expect Fe plus, and if we're comparing Fe plus and Fe3 plus, this has a smaller positive charge, so this should be larger. So that looks like it's going to be a true statement. So that's likely going to be our answer choice. That also eliminates choice E. Let's verify that C and D are false and that we can exclude them as answers as well. So choice C is comparing ionization energies again, S2 minus and Cl minus. And again for this, because they're anions, because they're not neutral atoms, we have to not just think about periodic trends, but we have to account for how many protons and electrons they have. So if we go to the periodic table, S2 minus is number S is number 16, so S2 minus has 18 electrons and 16 protons. Cl minus also has 18 electrons. We add one electron to that, still has 17 protons. All right. So again, for ions especially, when we're talking about ionization energies and other periodic trends, it's helpful to think about subatomic particles. So this has 18 electrons and 16 protons. This one has 18 electrons and 17 protons. And so once again, the one that has more protons in the nucleus, which is chlorine, we would expect to have the higher ionization energy. Because if it has more protons in the nucleus, it's going to hold on to the electrons tighter. There's a stronger attraction between protons and electrons, and that then leads to a higher ionization energy. So this one is also false because S2 minus should be smaller than Cl minus in terms of ionization. And then finally here we're looking at atomic radius of lithium and cesium. This one is a pretty straightforward comparison. So Li and Cs. Li is number 3, Cs is number 55, but they're in the same column. As we go down the column, the radius gets larger and larger because we're adding more subshells to the valence electron configuration. So cesium has filled 6s, whereas lithium is only 2s subshell for the outer electrons. So we would expect cesium to be much larger. Remember, as we go to higher period numbers or higher values of n, the principal quantum number, the radius tends to get larger. So cesium has a larger radius than lithium by quite a bit. This one says, choice D says that the atomic radius of lithium is larger, so that one is also false. All right, so only one true statement, which is letter B in this case. All right, next one is also closely related to this. Last one that was a request from a student. Consider the following ordering. So we're going from smallest to biggest. We want to know which of these gives a correct trend for ionization energy. So again, we're dealing with ionization energy. Now these problems are difficult because we have 4 statements to sift through and figure out which combination of them is correct and incorrect and all that stuff. It is helpful to take them one at a time, and if you're very sure about one, look at answer choices that help you eliminate those. So I think, given some things we've already talked about in this review, choice 1 is a very easy comparison. So if we have Na+, magnesium 2+, aluminum 3+, silicon 4+, let's figure out, again, these are ions, so if we're talking about ionization energy, let's first figure out how many electrons they have and figure out then how many protons also. So we have Na+ would have 10 electrons and 11 protons, magnesium 2+, take away 2 electrons, that's 10 electrons, aluminum 3+, take away 3 electrons, that's 10 electrons, silicon 4+, take away 4 electrons, that's also 10 electrons. So all 4 of those cations have exactly 10 electrons. They have the same configuration as neon. All of those then involve removing core electrons from the neutral element, so they're all the same in that regard. So in terms of number of electrons, we have all of them have 10 electrons. But then we have to think about which of these have different numbers of protons. So if they all have 10 electrons, the number of protons is still just the atomic number. So that's going to be 11 protons for sodium, 12 protons for magnesium, 13 protons for aluminum, and 14 protons for silicon. So if we have 4 cations that are isoelectronic, meaning they have the same number of electrons, the one that has the highest ionization energy is going to be the one that has the most protons, and so the ionization energy will track with number of protons. So we would expect this order to be correct. 11 protons, 12, 13, 14, ionization energy sequentially increasing. So this one is going to be correct. And so if we're certain in that answer choice, which I am, I hope you are too at this point, we're certain that that answer choice is correct, we can eliminate choice A, we can eliminate choice B, we can eliminate choice E because these 3 answer choices don't include number 1 as one of the options. So like I said, sometimes you can use a little bit of game theory here to help yourself eliminate answers and at least get closer to the right answer even if you have some uncertainty. Choice number 2, beryllium, magnesium, calcium, strontium. These ones are all in the same column of the periodic table as we'll see. Beryllium, magnesium, calcium, strontium. The ionization energy should decrease in that order. Beryllium should be higher than magnesium, which is higher than calcium, higher than strontium. So we should get a lower and lower ionization energy as we go down. That's the opposite of what's written. So this one is incorrect. We've already eliminated answer choice B because it doesn't include number 1, and this further verifies that answer choice B can't be correct because number 2 is the wrong order. Number 3 here we're comparing halogens, iodine, bromine, chlorine, fluorine, also all in the same column of the periodic table. So if we go back to the periodic table, that's these 4 elements here, and this time we're saying that the ordering is that iodine is the smallest, bromine, then chlorine, then fluorine is the largest, and that is the correct order. Ionization energy increases as we move up a column from bottom to top. So this one is also correct. Those come in the right order, I, B, R, C, L, F, and so that's going to be one of our answer choices. And again, number 3 should be correct, so if we're certain about that, we could eliminate answer choice C already because that doesn't include 3, and we could anoint D the winner. Let's verify then that choice 4 is also correct. So here we're doing aluminum, silicon, phosphorus, chlorine. Those are all in the same row of the periodic table as we'll see, aluminum, silicon, phosphorus, chlorine, and we are moving right to left. Aluminum, then silicon, then phosphorus, then chlorine, so this one should be bigger, bigger, and even still bigger. So that's the correct ordering. We skipped group 6 here, and if you think about group 6, which is sulfur, sulfur would be between phosphorus and, would be smaller than phosphorus and chlorine. So this is where we have that dip in the trend. So aluminum to silicon, the ionization energy increases. Silicon to phosphorus, the ionization energy increases. Phosphorus to sulfur, it would decrease, and then sulfur to chlorine would go back up. But we skipped sulfur, so the ionization energy definitely increases as we go through 13, 14, 15, 17 in terms of atomic number. So this one is also correct. We've already identified that this is the correct answer, D, based on the other two, but we can verify that that's correct. So 1, 3, and 4 are all the correct orders in this case. All right, the last few questions deal with questions that we had trouble with based on the results of the homework assignment. And so what we have here is which of these is the 2p subshell lowest in energy? And I think this question was a little bit easier than we may have thought at first. And I didn't really cover it in this exact terminology in class, so I understand why there was some confusion. So if we're comparing the same subshell in different elements, more protons, or in other words, larger Z, correlates with a lower subshell energy. So remember, subshell energies are all defined as sort of negative terms because it's dealing with the attraction between protons and electrons, which is defined as a negative energy of interaction. But if you have more protons, you have a lower subshell energy. That kind of comes from the Bohr model. So remember, the Bohr model said that the subshell energy was related to negative Z squared. So as you add more protons, the subshell energy gets more negative by a square of the Z term. It's not quite that simple. These are all multi-electron elements, so the Bohr model doesn't apply, but the trend is still true. As we add more protons to the nucleus, we would expect a given subshell to get lower and lower energy. It doesn't really matter how many electrons they have in them or where they are in the periodic table. The 2p subshell, which all of these would have, whether they're occupied or not in the ground state, the 2p subshell will get lower and lower in energy as we add more protons to the nucleus. So we have lithium, beryllium, boron, carbon, nitrogen, and those elements all just come in order. So lithium is atomic number 3, beryllium number 4, boron 5, carbon 6, nitrogen 7. That means they have 3, 4, 5, 6, 7 protons respectively. So this is going to be Z equals 3, Z equals 4, Z being the number of protons in the nucleus, of course, Z equals 6, Z equals 7. So that's the order that they come in. So the one that should have the lowest subshell energy is choice E, nitrogen. This was the question we did worse on. I think we probably thought about it a little bit too hard. We're just comparing the energy of an orbital or a subshell, which is dependent on the number of protons in the nucleus primarily. All right, the next couple will deal with ground state electron configurations. So this one asks us to, we want to give the full ground state electron configuration, the symbol, and the group number using the valence orbital diagram. So our valence orbitals in this case are going to be 2s2, 2p3. So if we go to the periodic table, the valence electrons are 2s2, 2p3. So the electrons that come before that are going to be 1s1, 1s2, or what we would abbreviate as the helium configuration. So the configuration for this guy is going to be helium as the core, and then 2s2, 2p3. So all of these have the correct configuration listed. So none of these are going to have the wrong electron configuration. The second part is to identify what element this is, and that's going to eliminate a lot of our answer choices because these four all have different elements listed. So there's two ways to do this. This corresponds to a total of 7 electrons, 2 from helium, and then 2s2, 2p3, so a total of 7. And so we go to the periodic table, the neutral element that has 7 electrons is atomic number 7, which is nitrogen. Or alternatively, we said that the valence electrons were 2s2 and then 2p3, so 2p, 1, 2, 3 takes us to nitrogen. So by a couple of different arguments, we identify that nitrogen is the element, so that eliminates choice A, which is boron, choice B, which is phosphorus, choice D, which is arsenic, and so the only one, and I misspoke earlier, they don't all have the correct electron configurations. I was looking at this too quickly. So this electron configuration is correct, but this one is wrong because the core should be helium and not neon. So this has both the wrong electron configuration and the wrong element. I apologize for that misspeak earlier. Same one here. This has the wrong core electrons. It wouldn't be argon core electrons for 2s2, 2p3. It would be helium core electrons. So again, wrong configuration and wrong element. Now we have this choice here, which has the correct electron configuration, the correct atomic symbol. Now we just need to look at group number. Now there are two systems for numbering group numbers. Maybe this nomenclature we use is a little bit confusing. What we gave here were the two alternative group number types of conventions. So one is the A-B system, where you have group numbers 1 through 8, and they have A's or B's next to them to indicate main group versus transition elements. And then you also have just the straight up, and these sometimes use, the A-B system often uses Roman numerals, but it could be, or Arabic numerals. So that means either the Roman or Arabic numerals are fine. And then the regular system, the new system, is just, uses just straight up Arabic numerals. And you just number left to right 1 through 18 as you go through the columns of the periodic table. So there's two ways of numbering the groups in a periodic table, and we give you both of them here as alternatives. Now, if we go to the periodic table that you guys have at your disposal, our periodic table has the old school system, which has the A and B numbers. The nice thing about this system is that for the A groups, the group number, as we said, gives you the number of valence electrons, so it's useful. So if we find nitrogen, nitrogen using the old system is in group 5A. Using the new system, which is just numeric, we would number left to right. So this is group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in the old system, nitrogen is 5A. In the new system, it's group 15. So we see that the numbers given for this answer choice are 7A, 17. So this one has the wrong group numbers. So a lot of you picked this answer, but it has the correct configuration. It has the correct atomic symbol, but it has the wrong group number, so this answer choice is also out, meaning the only answer that works is none of these. And again, there's a psychological barrier to picking none of these that I recognize may be part of the reason why we got this wrong, but that's going to be the only answer that works here. All right. This question, I think, we didn't do so hot on it, but I think part of it was just that it was worded pretty poorly. So according to the Aufbau Principle, which of these describes the type of subshells being filled in a set of elements below? Aluminum, neon, titanium, iodine. Now, I think what this question was getting at, and we should have worded it better, is that we're looking for the subshells being filled last. So in other words, where does that last electron go, that last valence electron go, as we're doing electron configurations for these? And that's just going to come from the location on the periodic table. So we do need to know the atomic symbols. Aluminum is Al, neon is Ne, titanium is Ti, iodine is Z is number 53, so we gave you the atomic number. We only expect you to know the first 36, that's why we gave you the atomic number for iodine. The symbol for that is I, so that's what we're going to look at the periodic table, these four elements. And we just need to figure out, for these four elements, what is the last subshell that is filled, and that's from their location on the periodic table. So we find aluminum, Al. Aluminum is in the third row of the periodic table, and this is going to be 3s and then 3p. So the last electron in aluminum goes into the 3p subshell. So aluminum, we're going to be filling p subshells last, a p subshell, 3p last. Neon, if we go to the periodic table, is here. This is the second row, and this is the p block. So the last electron for neon goes into the 2p subshell. So neon would also involve filling a p subshell. Titanium, which is Ti, is here in this middle section of the periodic table. So the last electrons that go into titanium, we have argon as the core. This would be the fourth row, so it's going to be 4s1, 4s2, and then we go 3d1, 3d2. So the last subshell filled in titanium is 3d, or more simply a d subshell. And then finally for iodine, iodine is down here in the fifth row of the periodic table. So the noble gas before it is krypton. We then have 5s2, 4d10 to go through the whole D block, and then we're back in the 5p. 5p1, 5p2, 5p3, 5p4, 5p5. So the last electron in iodine goes into the 5p subshell, so it's also going to be a p subshell that's filled last. So the correct one for this would be choice A, which is p, p, d, p. Those are the last subshells filled in these. And I think the confusing wording on this was part of it. We're just looking again, where does that last electron go, which is determined by the location on the periodic table. All right, and then finally the last one, we're looking here for an orbital diagram reflects an atom not in the ground state. So there's two things we have to consider for identifying ground state electron configurations or orbital diagrams like this, Aufbau and Hund's rule. So Aufbau principle says we fill subshells lowest energy first and then to highest energy. So we have to fill them in the correct order. In these diagrams here, we have 1s, 2s, and 2p subshells, So that's going to be, we use the periodic table to figure out the order, so it's 1s, then 2s, then 2p. So that's the order they come in. And so that means if all of these are going to obey the Aufbau principle, we need to fill the 1s first before we start adding electrons to the 2s, and then we need to fill the 2s before adding electrons to the 2p. Remember, each of these orbitals can hold 2 electrons. That's when it's considered filled, is when it has 2 electrons in it. Each arrow represents an electron in this diagram. And in all of these diagrams, we see that they have completely filled 1s, they have completely filled 2s, and then they have partially filled 2p. So all of these are going to obey the Aufbau principle. So none of these configurations disobey the Aufbau principle because they all fill the 1s and the 2s before putting electrons in the 2p. So then what's going to allow us to identify which of these is and is not a ground state is to look at Hund's rule. Really, there's more than one Hund's rule, but we'll just call it Hund's rule for now because we only need to worry about the one in this class. And Hund's rule states that we want to maximize the number of unpaired electrons. So remember, an unpaired electron is one that has a certain spin, spin up, or spin down, that does not have an electron with the opposite spin somewhere in that configuration. So we're looking for a maximum number of unpaired electrons. What this means more practically is that if we're filling degenerate orbitals, so the 2p orbitals are degenerate orbitals, there's 3 of them all at the same energy. When we're filling these 2p orbitals, we put 1 electron into each orbital first, and those electrons have to all go in with the same spin before we start pairing them up. Alright, so let's look at then which of these choices follow that rule. So the first answer choice looks like it's correct for us. So it has 3 2p electrons. We put 1 in each orbital. All of them have a spin-up configuration, so this one works out well for us. 3 spin-up electrons all in the 2p. If we go to the second one here, some of these threw us off because remember that we don't necessarily have to fill the orbitals left to right. All 3 of these 2p orbitals are at the same energy, and spin up and spin down just for 1 electron doesn't have an impact on the energy either. So even though we can eventually go left to right, spin up first, it doesn't have to be that way. So if we have 1 electron in a 2p orbital, which is what we have in this configuration, this 1 electron could go into any of these 3 orbitals, and it could be either spin up or spin down. All of those are equivalent. So no matter how we do it, this is a ground state. So for 1 2p electron, there's really no arrangement of spin or orbital that's wrong. For this configuration here, we have 2 electrons. They go into each into 1 orbital, each with spin up. So that follows Hund's rule. This configuration here caused a little bit of a problem. So we have 4 electrons this time. The first 3 we would put into separate orbitals with the same spin. And now this 4th electron we have to pair up with one of these. But again, it does not matter where this 4th electron goes. It has to be spin down to follow Pauli exclusion, which is another one that we have to think about. Pauli exclusion would say that if we have 2 electrons in 1 orbital, they have to be opposite spins. All of those are fine. So we should also say that all of these configurations follow Pauli exclusion principle as well, which is that no 2 electrons can have the same quantum numbers. So to follow Pauli exclusion principle, this electron has to be spin down, but it doesn't matter if it goes into the 1st, 2nd, or 3rd orbital. All of those are the same energy. So this one also works as a ground state configuration. This 4th electron can go into any of these 3 orbitals, and that'll satisfy Hund's rule. And then finally, the last one here, we have 3 2p electrons, but we have the first one up, 3rd one up, but the 2nd one down. So this does not maximize the number of unpaired electrons. If we have 3 electrons, we should have 3 that are unpaired, all in individual orbitals. This one we only have 1 unpaired electron because this spin-up electron has a spin-down counterpart, so we're not maximizing the number of unpaired electrons in this configuration. So this is not a ground state, and this answer choice would be the one we pick. I think these were given letters, so this would be choice E, I guess it is, but that's one that's clearly not a ground state. Alright, that takes us to the end of this review. I apologize for the delay in getting this because of messing up the video the first time. So if you have any remaining questions on this assignment, we're getting close to exam time, so please come and find me with those questions either by email or in person, and I'd be happy to go over any of these problems in more detail or other Chapter 2 homework problems that you're still not clear of. Alright, thank you for watching, and I will see you guys in class this week.